A Finnish startup has just made a bold announcement, claiming to have developed what they call the world's first production-ready solid-state battery. According to them, it can handle 100,000 charge cycles, fully charge in just 5 minutes, operate in temperatures ranging from -30 degrees Celsius to +100 degrees Celsius, and deliver an energy density of 400 watt-hours per kilogram. They also say it uses no lithium or rare earth materials and that they're already manufacturing it at gigawatt-hour scale. If you're new to the channel, make sure to subscribe and hit the bell icon so you don't miss future updates. Watch the full video and share your thoughts in the comments. Now, if even half of these claims are true, this would completely eliminate EV range anxiety. It would make current lithium-ion batteries obsolete and transform industries like grid storage, electric aviation, and military power systems, all from a company that's only about 18 months old. But when you compare these claims to what physics allows, and then look at how Donut Labs' own technology partner described the device internally, the story starts to shift. In this video, we'll go through each claim step by step. We'll look at what independent battery experts said after visiting their booth, trace the origins of the technology, and rely on the numbers to tell the real story, because those numbers reveal quite a lot. Donut Lab Oy was registered in Estonia in August 2024, making it a relatively new company. Its CEO, Marko Latari, comes from a computer science background. He's best known for founding AppGyver, a no-code development platform that was acquired by SAP in 2021. He's also involved in another venture claiming to build the world's first true AI superintelligence. However, there's no visible background in battery engineering, electrochemistry, or materials science. His brother, Tuomo Latari, founded Verge Motorcycles. Their hub motor, known as the Donut Motor, is a real and impressive piece of engineering. However, since 2018, Verge has delivered fewer than 100 motorcycles. The technology works, but scaling it has been a challenge. At CES in January 2026, Donut Lab unveiled what they called a production-ready solid-state battery. But what was actually shown at their booth raised questions. The displayed units appeared to be 3D printed cases with no working cells or functional prototypes, essentially plastic shells designed to look the part. Professor Shirley Meng from the University of Chicago, one of the world's leading researchers in solid-state batteries, visited the booth. Her assessment was blunt. "They have zero demo, so I don't believe it." While that's just one opinion, it begins to form a pattern. Looking at the financial side, Donut Lab has raised around 40 million euros so far, with no major institutional investors publicly disclosed. Finnish broadcaster Yle reported that the company shared investor materials promising tenfold returns within 18 months to small retail investors. That's unusual. Companies with truly groundbreaking battery technology typically attract interest from major players like Toyota, BMW, or DARPA, rather than reaching out to small investors. There's also the issue involving PwC. PricewaterhouseCoopers, one of the world's largest audit firms, was hired to audit Verge Motorcycles, Donut Labs' sister company and exclusive motorcycle partner. However, they were unable to complete the audit due to missing records, including inventory management data, sales receipts, and documentation for 2.6 million euros in development expenses. As a result, PwC issued a refusal to express an opinion, the most serious type of audit outcome. Now let's turn to the technology itself, because this is where things become particularly interesting. Donut Lab isn't developing this battery entirely in-house. About 10 weeks before the CES announcement, in October 2025, the company made a significant investment in a Finnish nanotechnology startup called Nordic Nano Group. As part of the deal, Marco Latari joined Nordic Nano's board. Nordic Nano was also founded in 2024. According to its financials, the company reported 50,000 euros in revenue, a net loss of 202,000 euros, and a team of just 3 employees. Their facility is located in a converted department store in Imatra, Finland, covering roughly 3,800 square meters. At the same time, Donut Lab's CEO claimed they were already manufacturing at gigawatt-hour scale. For context, building just 1 gigawatt-hour of battery production capacity typically requires between $80 million and $150 million in investment, along with hundreds of specialized engineers. Nordic Nano, by comparison, has 3 employees and minimal revenue, making those manufacturing claims difficult to reconcile. Now here's the detail that changes how we should interpret everything else. Nordic Nano didn't describe their device as a solid-state battery. Instead, they called it an electrostatic bipolar supercapacitor. The specifications they shared, 400 watt-hours per kilogram over 50,000 cycles, remain the same, but the category of the device is completely different. And that means the underlying physics is different too. This distinction wasn't just internal. It was independently confirmed by sources like Inside EVs, Bike-EV.com, and Captain Electro. A battery and a capacitor are not just 2 names for the same thing. They work in fundamentally different ways. Batteries store energy through electrochemical reactions, where ions move through an electrolyte and embed themselves into electrode materials. Capacitors, on the other hand, store energy electrostatically, holding charge on the surface. That difference matters a lot when it comes to what the device can realistically achieve at scale. So the real question becomes, what is this device actually? And interestingly, you can answer that by looking purely at the specifications. There are several independent clues that point in the same direction. Start with the cycle life. The claim is 100,000 cycles. For comparison, the best lithium iron phosphate batteries, known for their durability, typically reach around 10,000 cycles before dropping to 80% capacity. Even CATL, the world's largest battery manufacturer with massive R&D resources and a huge workforce, generally achieves about 10,000 to 12,000 cycles with this chemistry. Supercapacitors, however, routinely reach anywhere from 500,000 to 1 million cycles. So where does 100,000 cycles fall? Much closer to capacitor performance than battery performance. Next, look at charging speed. A full charge in 5 minutes implies roughly a 12C charge rate. Most lithium-ion batteries start degrading quickly above 3 to 4C because lithium ions begin plating onto the anode instead of properly integrating into it. That's not just an engineering issue. It's a hard physical limit. Capacitors, by contrast, can charge in seconds. A 12C rate is trivial for them. Now consider the temperature range. The claim is operation from minus 30 degrees Celsius to plus 100 degrees Celsius with over 99% capacity retention. Standard lithium-ion batteries typically operate between minus 20 degrees Celsius and 60 degrees Celsius, and charging below freezing can cause permanent damage due to lithium plating. Supercapacitors, however, commonly operate in a wider range, roughly from minus 40 degrees Celsius up to 65 degrees Celsius or even 85 degrees Celsius. Again, the claimed performance aligns more closely with capacitors than batteries. Then there's the voltage. The device is said to operate at a maximum of 4.2 volts. That number is very specific. It's the standard upper limit for lithium-ion chemistries like NMC and NCA, where the material structure becomes unstable beyond that point. Non-lithium chemistries don't naturally operate at exactly 4.2 volts. Sodium-ion batteries, for example, typically top out closer to 3.8 to 4 volts. When questioned about this, Donut Lab reportedly said the voltage could be adjusted based on customer needs. But that's not how electrochemistry works. Voltage is determined by the material properties, not by preference. Another interesting claim is shape flexibility. The company says the cells can be made in almost any shape, including irregular forms. Traditional batteries are built using either rolled or stacked structures, which limits their geometry. Nordic Nano, however, uses a manufacturing method involving screen printing carbon nanotube-based materials onto conductive surfaces. This approach can produce highly flexible shapes, which is consistent with pseudocapacitor design, but not with conventional batteries. Each of these points, taken individually, suggests the same thing. Put together, they strongly indicate what kind of device this really is, even before considering the company's own terminology. Finally, let's look at one of the most important claims. Energy density, 400 watt-hours per kilogram. For a purely electrostatic capacitor operating at 4.2 volts, reaching that level of energy density would require materials far beyond anything currently known. In reality, such capacitors are limited to around 0.1 watt-hours per kilogram. That's not an engineering challenge, it's a fundamental physics limit. However, there is another category called pseudocapacitors. These store energy through fast surface-level redox reactions rather than purely electrostatic charge. Because of this, they can achieve much higher energy densities. In fact, a study published in January 2025 by the Korea Institute of Science and Technology demonstrated a pseudocapacitor using a carbon nanotube and polyaniline composite that reached 418 watt-hours per kilogram with a cycle life of 100,000 cycles. Those numbers are strikingly similar to what Donut Lab is claiming. But there's an important detail. In that research, the 418 watt-hours per kilogram figure was calculated based only on the active electrode material, not the full device. Once you include the weight of packaging, current collectors, electrolytes, and housing, real-world energy density is typically 4 to 10 times lower. To really understand how extraordinary these claims are, you need some context. What are the most well-funded and technologically advanced organizations in the world achieving right now? Take QuantumScape, for example. Backed by Volkswagen and Bill Gates, with over $600 million in funding and 15 years of focused development, they only reached pilot production in early 2026. Their independently validated cells deliver about 301 watt-hours per kilogram and just over 1,000 cycles with 95% energy retention, not 100,000 cycles. That's what 15 years and massive funding have produced at the cutting edge. Toyota has spent decades working on solid-state batteries with thousands of researchers involved. Their target for mass production is still around 2027 to 2028. Even Toyota, holding more solid-state battery patents than any other company, has never claimed anything close to 100,000 cycles or a full charge in 5 minutes. Then there's CATL, the world's largest battery manufacturer. With 150,000 employees, $11 billion in R&D investment, and tens of thousands of patents, they have over 1,000 researchers focused solely on solid-state batteries. Their best commercial lithium iron phosphate battery achieves around 205 watt-hours per kilogram at the pack level. They've announced a condensed battery with a claimed 500 watt-hours per kilogram at the cell level, but it hasn't been independently verified and isn't in mass production. Factorial Energy has delivered cells at 391 watt-hours per kilogram to Mercedes. They've built real prototypes, including a vehicle that reportedly drove 749 miles on a single charge. And even with real automaker partnerships and functioning cells, they're still years away from full commercialization. Now compare all of that to Donut Lab, an 18-month-old company with 40 million euros in funding, no approved patents, no disclosed chemistry, and a technology partner with just 3 employees and 50,000 euros in annual revenue. The gap between that and what companies like QuantumScape have achieved isn't just large. It's an entirely different category of claim. To be fair, there is some real evidence. VTT Technical Research Center in Finland, a credible government-backed lab, did test a physical cell provided by Donut Lab. They confirmed 2 things. The cell could reach 80% charge in about 4.5 minutes at an 11C rate, and it could operate at temperatures between 80 degrees Celsius and 100 degrees Celsius. So yes, a real physical device exists, and it performs impressively in those specific areas. But here's what VTT did not verify. They didn't measure the cell's weight or size. They didn't determine the chemistry. They didn't calculate energy density. They didn't test long-term cycle life. And they didn't confirm whether the device contains lithium. In fact, the test procedures themselves were defined by Donut Lab. The 2 results that were verified, fast charging and high temperature operation, are also the easiest to demonstrate and happen to align closely with how capacitors behave. So what would it actually take to prove the bigger claims? An independent lab would need to weigh the cell, measure its total energy capacity, and calculate watt-hours per kilogram. That's how real energy density is determined. To validate a 100,000 cycle lifespan, even with aggressive testing at a 12C rate, you'd need nearly a full year of continuous testing. There's no shortcut for that. Confirming whether lithium is present would only take a basic material analysis, something that can be done in a single day. Verifying solid-state construction would require cross-sectional imaging, which is standard practice, and confirming large-scale manufacturing would simply require journalists or auditors to physically inspect the production facility. As of March 2026, none of these critical verifications have been completed. The Verge motorcycles that are supposed to use these batteries were originally scheduled for delivery in the first quarter of 2026, but that timeline has already slipped into April. Once production bikes are delivered and independent engineers can take them apart, the chemistry will become clear. That will be the real test. So where does all this leave us? Even before looking at the business side, the physics tells a consistent story. A device that charges in 5 minutes, lasts 100,000 cycles, operates across extreme temperatures, handles high current without voltage drop, and can be shaped freely. That description fits a capacitor. Calling it a battery doesn't change how it actually works. And notably, Nordic Nano, the company behind the technology, referred to it as an electrostatic bipolar supercapacitor in their own materials. The most likely explanation is that this is a pseudocapacitor based on carbon nanotube composites, similar to what's been demonstrated in academic research. The claimed 400 watt-hours per kilogram is likely based only on the active electrode material, not the full packaged device. In real-world conditions, once you include all components, the actual energy density would be significantly lower. So the solid-state battery label appears to be more of a marketing choice than a technical one. That doesn't necessarily mean the technology has no value. A pseudocapacitor with fast charging and long cycle life could still be very useful in certain applications. But it's a different type of device, with different physics and very different expectations at scale. And that distinction really matters. So what should you watch going forward? Keep an eye on the delivery of Verge motorcycles. If and when production units ship, independent teardowns will reveal the true chemistry. VTT's cold temperature testing results are still pending, and eventually, independent measurements of energy density will confirm whether the 400 watt-hours per kilogram claim holds up. Until then, trust the data, not the slogans. If this kind of evidence-based breakdown of energy technology is what you're here for, Consider subscribing and share your thoughts in the comments. Do you think this is a battery, a capacitor, or something else entirely? I'll see you in the next one.